Well, hello again. We're back here. This is another video on Chapter 7. This will be our second method. Hopefully you've seen the other ones on the introduction and the first method we talked about, which is direct integration. So today we're going to talk about a different method, another so-called geometric method. So let me switch over and start my, share my screen. Oops, sorry, didn't put that away. And let's get up here, and here we go. All right, so today, again, we're talking about deflections. We're going to talk about what's called the conjugate beam method. Conjugate beam method has been attributed to many different engineers, structural engineers, but the two that get the biggest credit are called, or were Heinrich Müller-Breslau and Christian Otto Moore. So Müller-Breslau was born in 1851. There's a picture of him. And in 1875, he opened a civil engineering office in Berlin. And he is known to found the so-called Berlin School of Structural Theory. You got to remember, this is the 1870s. There's really no analytic computers. There's really no computing devices besides individuals. So being able to get good, reliable approximations quickly were the backbone of structural engineering. And both Müller-Breslau and Moore were very good at graphical techniques, kind of shortcut solutions that got reliable and good approximations. So Moore, again, is really known for a lot of visual work, and you might remember from your strength of materials work, Moore's circle, a graphical method. Of course, all these things can be done computationally now with your computer or your calculator, just more efficiently, but these are good backbone techniques. And he did a lot of work, as you can see, in truss displacements and indeterminate work. And he is the Dresden School. And these guys were competing, really, and they had a lot of differences of opinion growing up in the day. And they both had very interesting facial hair, which good at the time. So these are the two guys that really set the footing for a lot of structural analysis and structural engineering that we still use today, see 150 years later. Okay, so conjugate beam method. What the conjugate beam is, or actually the conjugate is like a different space. So it's an imaginary beam, has the same dimensions as our real beam, we'll call it. But the loading on the original beam, whatever that was, is replaced with what we call the bending moment divided by EI, M over EI. And we'll talk about where that comes from in just a second. So once you do that, you can have this beam with this interesting load on it, and then you can use all the techniques that we've done so far. You can look at the shear and moment in that beam, except in the conjugate beam, shear force and bending moment map to slope and displacement in the real beam. So this gives you another technique of calculating slope and displacement that uses skills that you developed in shear moment diagram problems, shear moment at a point, even writing shear moment as functions. So all you have to do to work this method is just know statics and be familiar with how it's implied or applied. So really, let's talk about the similarities between loading and shear moment. Now you're already all of you are familiar with the relationship between load W and shear. We've used this to construct our shear moment diagrams. And of course, once you know the shear, you can use this relationship to construct the moment diagram. And a quick substitution will reveal that there is a second derivative of the moment will be equal to the load. Of course, then there's the integral approaches. And what you see on this slide is just everything we've already done for shear force and bending moment diagrams. So this technique's really going to rely on that. So those expressions we talked about before for shear moment were for the applied load, but now for slope and displacement of our beam, we know that they're related to load through these expressions. And these expressions that you see here are the ones that we derived in the previous video. So this is really our simple beam theory, which we related moment to displacement. And of course, the derivative of load would be slope, and again, how you see slope is related. And of course, we can enter it, and as you see this bottom equation here, that's the direct integration method that we already know. So far, that's just a review. So how are we going to put all this together? Well, let's compare shear and slope. So we know that the first derivative of slope is equal to the load, and we also know that the derivative of slope is this equal to m over EI. So what do you see? Well, you'll notice on the right-hand side of the equation, there's some kind of load, and it's related to shear. And over here, there's some kind of moment divided by EI, which could be thought of as a load, and it's related to slope. So really, if I were to replace load with m over EI, I could then have this same relationship between the loading to get the shear, and that would be the shear in the conjugate beam. But shear in the conjugate beam will be slope in the real beam. And the same thing can be done if you look at moment expressions. We know the second derivative of moment is the load, and the second derivative of displacement is m over EI. Again, you'll notice the right-hand side, load and moment, play the same role as in shear and slope, and then they also then relate back. So we know the load is related to the moment, and this m over EI is related to that. So really, if I could treat this guy over here as some kind of load, then I could predict displacement. And remember, that's our ultimate goal. Oh, I got a little ahead on my question there. So I already told you what we see before I asked you the question. So we're going to use this relationship to construct a beam that's the same length. And this beam will have a different possible set of conditions or supports, and that will be called the conjugate beam. And then we will put on the conjugate beam the real moment in the beam divided by EI as a loading on the conjugate beam. And then once we do that, slope and displacement in the conjugate beam will be, shear and moment in the conjugate beam will be slope and displacement in the real beam. So again, we have a real beam with a real load. I can take that beam and find the moment. And if I apply the moment from the real beam to the conjugate beam, in that conjugate beam space, the shear and moment in this beam will be the slope and displacement in the real beam. So those become our two fundamental concepts. So the two theorems are, one, that slope at any point in the real beam will be corresponding to the shear in the conjugate beam. So we get all into conjugate space and we do our work in finding shear and moment in the conjugate beam. That will map back to slope in the real beam. And then when we find moment in the conjugate beam, that will map back to displacement in the real beam. So this method relies on two things. One, that you can draw the conjugate beam, find the real moment, which I hope you can. We've been doing that for a while now. And then apply that as load to the conjugate beam, and then find shear moment again. So the first thing we have to do is, how do we build the conjugate beam? Well, that comes from what we call the conjugate beam supports. So we want to make sure in the conjugate beam that shear and moment in the conjugate beam match to slope and displacement in the real beam. So we'll do that by examining our typical support. So let's start with a real support, which would, the first one we can start with would be a pin. And I know in a pin connection that, or a roller, that I have no displacement at the pin, but I do have slope. So you can see 0 displacement, some slope. So now I have to think of what the conjugate beam what would give me something where that has 0 moment and shear? Well, that would be an external pin again. So an external pin also has no moment and has some shear. Oops. So you can see then that the displacement maps to the moment, and here the slope matches to the shear. So really the main thing to take from this is that a pin or a roller on the end of the structure maps to a pin or a roller in the conjugate beam. All right, let's examine this for other types of connections. So let's look at a free end. So what do we know about a free end in terms of slope and displacement? Well, we know they're not 0. We don't know what they are, but they're definitely probably not 0. So then we remember slope is moment. I mean, displacement is moment, slope is shear. So what kind of connection has moment and shear? Well, that would be a fixed connection. So again, you can see that 0 moment, non-zero moment, non-zero displacement, non-zero moment. I'll get it right in a second. Non-zero slope, non-zero shear. So again, the shortcut of this is a free end in a real beam maps to a fixed connection in the conjugate beam. And this works vice versa too. So if I start with the free end, which has no displacement and has no slope, well, in the conjugate space, that would become a free end. I may have said that wrong. You start with a fixed connection in real space, which no displacement, no slope, that maps to a free end in conjugate space, which has no moment and no shear. So now fixed maps to free. So let's do a quick summary. So external pins and rollers in conjugate space are internal pins and rollers, no change. Free end becomes fixed, fixed end becomes free. The third case would be an internal support. So now I have a pin or a roller that's internal in my beam. In that situation, I have no displacement at the pin, but I do have rotation. So what kind of support would have no moment, but shear? If you think about it for a second, it's an internal hinge. Because the hinge does not translate moment, but it can have shear on each end. So again, an internal support maps to a hinge. And of course, the opposite is true. If I have a hinge in my real beam, where I can have displacement and I can have different slopes, that will map to a pin connector or an internal roller, where I have moment and I have shear. So an internal hinge maps to a roller. So as a rule, these statically determinate real beams will be statically determinate conjugate beams. Statically indeterminate beams can be unstable. However, the loading, the M over EI's loading, can provide that equilibrium. So as a procedure, what we're going to do first is construct the conjugate beam and apply the real moment divided by EI as loading. Remember that a negative moment is negative load, negative is downward. Then we'll use our equations of equilibrium to find reactions, which would be the shear and moment. And then we can find internal values of shear and moment at any point we want. And remember, those map back to, so shear maps to slope and moment maps to displacement. Oh, got that out of whack, but you get the idea. So let's quickly draw some supports. So here's a structure, a real structure, and I want to map it to my conjugate structure. So I've got support here, 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 and here. So my end pin, remember our technique, end pins and rollers stay end pins and rollers. What about this internal hinge? Well, an internal real hinge maps to a conjugate roller. And now I've got an internal roller in the real beam that maps to a hinge. And then finally, I got my click got ahead of me there, but the final external pin maps to a pin. Now, don't get the idea that the beam just is a inverse or a mirror image of the other. It doesn't always work like that. So let's look at another one. So now here's a real beam. What's the conjugate beam look like? I've got three different supports I need to deal with. Let's start with the one here on the left. I've got a fixed connection. The fixed connection maps to a free. So that's no change. The internal hinge maps to a pin. And of course, my external pin maps to a pin. So now it looks like the real beam, quite complicated at the top. See at the bottom, it's a much simpler conjugate beam. So if this were my real beam in the bottom, then this would be my conjugate beam at the top. So again, a fairly simple looking beam can be quite sophisticated or quite challenging in conjugate space. So here's one that looks pretty straightforward. Simple span, a couple of overhangs. What's my conjugate look like? Well, I've got 1, 2, 3, 4 conditions. And as you already can see ahead, my free end is going to become fixed. My internal support is going to become a hinge. My internal pin is going to map to a hinge. And then of course, at the end, my free end is going to map to a fixed end. So that's a quite complicated scenario from the real beam to the conjugate beam. Okay, so this is an example coming up next. So I'm going to stop here and take a break. It's been a little bit long video, and then I'll come back with examples. So let me stop sharing and come back to you and let you know that, again, if you have any questions, make sure give me a call or give me an email and we can work it out. We'll try maybe to do a Zoom meeting later on next week or sometime that we can all get together. So until next time, take care.